All right, today we're going to put on our detective hats and solve a classic engineering puzzle. We're stepping into the shoes of a circuit diagnostician to get to the bottom of a defective logic gate. So let's just dive right in. In the world of digital logic, there is absolutely no room for maybe. Every single signal has to be a definite high, a 1, or a definite low, a 0. This whole binary system is the bedrock of all computing. But every once in a while, a tiny flaw in the design can trap a circuit in this weird, ambiguous state, a sort of digital no man's land. And that is exactly the problem we're going to be investigating. So the technology at the heart of our little mystery here is diode transistor logic, or DTL for short. And just like the name says, it uses a combo of diodes and transistors to do all its logical heavy lifting. This was a really foundational technology back in the early days of integrated circuits. And, understanding it gives us a fantastic peek into how digital electronics really got started. Now you might be asking, why DTL? Well, before DTL, there was RTL, resistor transistor logic. And DTL had this huge manufacturing advantage. See, on an integrated circuit chip, making a precise resistor is actually a lot harder than making a diode. So that efficiency made DTL a way more practical and, well, popular choice for building logic gates back then. Okay, let's get into it. Before we can diagnose a broken circuit, we need a baseline, right? We have to understand what a healthy one looks like. So our first subject today is a perfectly functional DTL NOR gate. Here's the schematic for it. We've got two inputs, A and B, and they feed into these diodes, D1 and D2, and those are connected to the base of our transistor, Q, which controls our final output, C. Our mission here is simple. We're going to trace the signal flow for every possible combination of inputs and just make sure this thing really does what a NOR gate is supposed to do. And here are the rules of the game. You can think of this as our forensics kit. These are the absolutely critical reference voltages for our components. A diode needs about 0.6 volts to start conducting. A transistor also needs 0.6 volts at its base just to turn on, but, and this is super important, it needs 0.8 volts to be pushed all the way on into what we call saturation. These numbers, they're going to be everything for our investigation. So let's start with case 1, inputs A and B are both low, both 0. Now, in this NOR circuit with low inputs, there's just no voltage to push current through the diodes to the transistor's base. They're both what we call reverse biased. With 0 current going to the base, transistor Q is in cutoff. It's completely off. It's basically an open switch. So the output C gets pulled up to 5 volts through that resistor. That gives us an output of 1. Perfect. Exactly what we'd expect from a NOR gate. Okay, case 2. A is low, but B is high. Now we're talking. With that high voltage at input B, diode D2 becomes forward biased. This creates a nice, clear path for current to flow right into the transistor's base. And this current is more than enough to shove transistor Q into full saturation. A saturated transistor acts like a closed switch to ground, pulling that output C all the way down to a 0. And if we run through all the other possibilities, we get this truth table. The output is a 1 if and only if both A and B are 0. That is the textbook definition of a NOR gate. This circuit works flawlessly. It's predictable, it's stable, it's reliable. This is our control specimen. And now for the main event. We're handed a new circuit, a DTL NAND gate. It's using the same building blocks, but the wiring's a little different. And here's the hook. We've been told there's something wrong with it. This gate is defective. At first glance, it looks a lot like the NOR gate, doesn't it? We've still got our 2 input diodes, we've still got our output transistor, but look closer. The really critical difference is how that base resistor, RB, is connected. It's now tied directly to the 5-volt supply. This subtle little change, this is the scene of the crime. And that brings us to a really crucial question in how transistors work. We know about cutoff, right? That's fully off. And we know about saturation, that's fully on. But what happens if a transistor gets just enough voltage to kind of turn on, but not enough to saturate? Well, it gets stuck in the middle. This is called the active region. And for a digital switch, it's a total disaster. And here's the evidence, the truth table for our defective gate. For 3 out of the 4 possible inputs, the transistor Q gets stuck in that dreaded active state, and the output is completely undetermined. It's not a 1, it's not a 0, it's just chaos. The only time it works is when both A and B are high. We need to figure out why. So let's start the forensic analysis. We're going to trace the voltages right through this faulty circuit and pinpoint exactly where things are going wrong. Let's just pick one of the failing cases, okay? Let's say input A is low at 0 volts. Because point C is connected to that 5-volt supply through the resistor, it really wants to be at a high voltage. This difference in potential across diode D1 causes it to become forward biased and start conducting electricity. Now, here's a key fact about silicon diodes. When they're forward biased, they have this characteristic voltage drop of about 0.7 volts. Since diode D1 is conducting from point C down to our 0-volt input, it effectively clamps the voltage at point C. So the voltage right there at C becomes exactly 0.7 volts. Okay, now this is the moment of truth. Let's bring in our forensics kit. The voltage at point C, which is also the voltage going to the transistor's base, is 0.7 volts. Now remember our rules. We need 0.6 volts to turn the transistor on. Well, 0.7 is greater than 0.6, so the transistor does turn on. But to drive it all the way into saturation, we need 0.8 volts, and 0.7 is less than 0.8. So there it is. That's the smoking gun. That 0.7 volts at the base is just enough to pull the transistor out of cutoff, but it's not enough to push it all the way into saturation. The transistor is stuck in this active region, acting more like an amplifier than a switch. And that means the output voltage isn't pulled cleanly to ground, it's just flowing somewhere in between, at some unpredictable level. Case closed. So, we found the defect. Now how do we fix it? Well, the solution is actually beautifully simple, and it demonstrates a core principle of good circuit design. You have to be the boss of your voltage levels. Here's the game plan. The whole problem is that 0.7 volts at point C is enough to tickle the transistor into turning on, so we need to raise the bar. We can do that by inserting one more component, a diode, we'll call it D3, right between point C and the transistor's base. This basically creates a higher voltage hurdle that the signal has to clear. Let's just do the quick math. To turn the transistor on now, the voltage at point C has to be high enough to overcome 2 voltage drops in a row, the 0.7 volt drop of our new diode D3, plus the 0.6 volt turn-on voltage of the transistor itself. So you add those up, and the new minimum turn-on voltage is now 1.3 volts. And this just brilliantly illustrates the fix. On the left, you see the defective circuit. On the right, our corrected version with that new diode D3 in place. Now, when an input is low and point C gets clamped at 0.7 volts, that voltage isn't even close to the 1.3 volts we need to turn the transistor on. So the transistor stays firmly in cutoff, which is exactly what it's supposed to do. And what's the result? A fully functional DTL NAND gate. If you look at its new truth table, if any input is low, point C is at 0.7 V, the transistor stays off, and the output is a clean 1. It's only when both inputs are high that the voltage at C can finally rise high enough to clear that 1.3 volt threshold, saturate the transistor, and pull the output down to a solid 0. It works perfectly. You know, this case just shows us that in circuit design, the smallest little details have the biggest consequences. The placement of a single diode, a component that costs maybe less than a penny, made the difference between a totally useless circuit and a perfectly working logic gate. It's just a powerful reminder that in engineering, precision is everything. So it makes you wonder, right? Where else in circuit design could a seemingly tiny change have such a massive impact?